Hello, welcome to Basics of FEA. This is the last day of the current week, which is the 5th week, and what we will discuss today is a little bit more detail about 1D heat conduction equation, and in this context we will discuss 1D equation related to Cartesian frame of reference, then also with respect to cylindrical and spherical frame of reference, and how do we actually implement boundary conditions through an actual example. So that is what we will do. So first we will write the equations for heat conduction with respect to different frames of references. So if we have a Cartesian frame of reference, then the 1D equation, and this we have seen it earlier also, is K A del T over del X plus A Q equals rho C A del T over partial of temperature with respect to time, and K is thermal conductivity, and its units are watts per meter per degree centigrade. Then A is cross sectional area, so to give you a context, suppose I have some bar, then the cross sectional area of this bar represents A. So that will be in meter square. Q is heat generated per unit volume. So it is watts per cubic meter. So to give you an example, if you have a wire and it is carrying current, then the total heat which will be generated will be I square R, right. So this is actually heat generated per unit volume per unit time per second. Okay. So the total heat generated will be I square R, and suppose the length of the wire is 10 meters, then I can calculate the volume of that wire, and I can divide this total power by the volume of the wire, and that will give me Q. Okay. Then rho corresponds to density, so that is in kilograms per cubic meter, and C corresponds to specific heat, and that is joules per kg per degree centigrade, or if I do a little bit more dimensional analysis on this, then I can also express it as meter square per second square per degree centigrade. So in this equation, this particular term relates to how much heat is getting transferred due to delta T, temperature gradient, how much heat is getting transferred due to temperature and because of conductive effects. Okay. This term represents how much heat is being generated. So it captures the effect of heat getting generated, and this is an equation also in time, and this term, it represents the effect of rise of temperature with respect to time. So if the temperature is not rising, then the del T over del partial of temperature with respect to time will be 0. So this is a very general equation for a 1D system. Now, for a cylindrical frame of reference, an example of a cylindrical system would be you have a cylinder, okay. So that's my cross sectional area A, and it is generating also heat along its entire length, and also there is heat conduction happening from one higher part to the lower part, and so on and so forth. So all the physical phenomena, heat transfer due to conduction, heat generated, and rise in temperature, everything is there. And for that, the governing equation is 1 over R So 1 over R partial of Kr times del T over del R plus Q, which captures the effect of heat generated per unit volume, times rho times C into del T over del T. Now, this particular equation is good if the overall length of the system, suppose this is L, then L has to be fairly large compared to, let us say, d out or outside diameter. Okay. This is the second equation, again 1D heat conduction equation, but this is for a cylindrical coordinate system. And then we have a spherical coordinate system. And an example of this kind of heat transfer would be that I have a small source of heat and it is surrounded by some homogeneous medium on all the sides. So, I am generating heat and it is spreading out in all directions uniformly. So, in that kind of a situation, the governing equation, one dimensional equation, is 1 over R square partial with respect to R, K R square partial of temperature with respect to R plus Q equals rho C partial of temperature with respect to time. Now, all these equations, they do not account for convective heat transfer. So, for instance, if you have this bar, it could be surrounded by air, right, and there may be not only heat transfer due to conduction, but also because of convection. So, air will pick up some heat and that heat will get dissipated into air. So, here we do not have a convective term in this entire equation. So, to account for convective heat transfer, and we will write the relation only for rectangular coordinate system, rectangular frame, and accounting for convection also. My governing equation is so the governing equation is pretty much the same, but we add one extra term, and the extra term on account of convection is P times beta times T minus T infinity, and I will explain that. So, to give you an example, suppose Suppose I have this fin, a thermal fin, and I want to see how temperature is changing in this thermal fin. And in this thermal fin, I have a heat source also, which is uniformly distributed, and the strength of this heat source is Q watts per square for per cubic meter. And then because of conduction, heat is getting transferred along the length. So this is my x direction. But also because it is surrounded by air, so heat is also getting dissipated due to convective transfer. So then that extra effect due to convection is captured by this term, and here beta is film coefficient or coefficient of thermal convection, and its units are in watts per meter square per degree centigrade. And then I have this term called P. So P is perimeter at position x. So what does that mean? So suppose I have this point P, then at this point that's my perimeter. Okay. So this differential equation is true at a point, right? Differential equations are always true at a particular point, and we have to find solutions on a point to point basis. So at that particular point P, this is the differential equation which governs it, and at that point I have to find P by actually measuring the fin, and I have to put that number in the differential equation. Okay. So P is known. P can vary with with respect to x, because here the fin is of a uniform cross section, but it can change. So P can be a function of x, but we know P. We know P. Now all these equations, this equation and the other two equations which we had developed, this equation and this equation, they all have this partial of temperature with respect to time. So this is for a system where we are looking for transient solutions, where solution is changing with respect to time. If the solution does not change with time, then it will be a steady state system, and a steady state system, partial of temperature with respect to time will be 0. So in this case, this term goes to 0. For a spherical coordinate system, this term goes to 0. For a cylindrical frame of reference, this term goes to 0. So if I just drop the temperature derivative of the time derivative of temperature, then I can get steady state equations for all these three coordinate frames. So for rectangular frame, okay, my governing equation, steady state equation, the governing equation is partial with respect to x, Ka del T over del x plus Aq equals P beta times T minus T infinity. By the way, I did not explain what is T infinity. So in this case, T infinity is the temperature of surrounding air. So it is temperature of air, and it is infinity because we are measuring this temperature quite far away from the fin. Temperature of air far away from the fin. So, that is my T infinity. If T infinity is small, then we will have more convective heat transfer. If it is more, then convective effects will be less. And beta is, as I explained earlier, it is film coefficient. So, that is my governing equation for the rectangular frame of reference. Now, what we will do is we will actually solve a problem, a 1D heat conduction problem, and where we will also explain how we incorporate this convective heat transfer condition into the overall differential equations. So, for rectangular frame of reference, we can express at element level right. At element level, my equation will be K E times T E equals F E plus some source term Q E, and the value of K I J will be integral over the domain of the element, which is 0 to H E K A So, these are all local coordinate systems. So, I have not x, but I have x bar. Okay. So, that is my K I J plus, now you see that this T is an unknown. So, we always typically move all these unknown primary variables on the left side. So, if I move this term P B times T here and I multiply this by weight function and integrate it over the domain, that will also be a part of K I J. So, there is a term related to K I J, and that is 0 to H E P times beta, and because we say that T temperature is equal to summation of T j psi j x, right. That is how we, this is for the eth element. So, I forgot. So, in this case, this will be equal to, the convective part will be psi j times psi I dx. This is all Rayleigh-Ritz formulation. So, weight function is same as psi, yes. So, by default we will be following Rayleigh-Ritz formulation in this whole system. Then my Fi, this equals 0 to He. So, F is the source term which relates to how much heat is being generated. So, that is A times Q times psi I dx, and then there is another source term which is related to T infinity, right. So, this plus 0 to He P beta T infinity. So, the formulation is exactly same. If we go back to our earlier lectures, the only thing which we have added is this P times beta times T minus T infinity, and when you find the residue, multiply it by a weight function, integrate it over the domain and do the weak formulation, you will get all these expressions. So, that process is exactly the same. And then Q1 E. So, suppose we have a two noded element, this is 1, this is node 2, and the length of the element is He, then Q1E equals minus Ka del T over del x at x is equal to 0. So, this is my local coordinate system, x bar is 0 here and it is He here, and Q2E equals Ka till T over del x at x bar equals He. So these are the element level equations. Now what we will do is we will actually, in our next lecture, we will assemble all these elements and then solve for an actual problem where we will specify the boundary conditions and see how we account for the actual 1D heat conduction equation in which we also have convective effects. So this closes our discussion for today, and we will continue this particular discussion in the next week, which is the 6th week of this particular book course. Thank you very much and have a great day.